All right, so what are we going to do today? Today we're going to talk about agents that plan ahead, and that's going to lead us into the first class of problems that we'll study in this class, which are state space search problems. We'll talk today in large part about uninformed search methods. These are things like depth first and breadth first search, which you've probably, most of you have seen these in some form. We'll talk about uniform cost search, which some of you have taken 170 have seen in another variant. And then we'll start talking about heuristic methods, which should be new to everybody. So last class we ended with a mystery. Let me show you the mystery again. Here's the mystery. The mystery is, how do you get an agent, say in a game like Pac-Man, to exhibit behavior that seems reasonably planned out and successful? So again, think about this setting, think about what this agent, what you see it doing, and what kinds of computations could give rise to this behavior. There's actually a lot going on here, not the least of which is kind of not sitting in the corner getting stuck or doing something that would be completely unsuccessful, right? And sometimes there's really fancy footwork. All right. So how do you get behavior like that? Well, we're going to actually spend the first part of the course answering that question. The first part of this course is about how to decide what action to take in a given circumstance. All right, so the first thing you might think is you might think about a very simple agent. And the simplest kind of agent is called a reflex agent. And what a reflex agent does is, rather than doing some complicated prediction of the future and some game theory, what it does is it simply chooses an action, kind of in a reflexive way, based on what it currently perceives from the world, and possibly some memory in case it kind of needs to track the world state. So a reflex agent might have memory of what's going on out of its vision. In a game of Pac-Man, there's no worry about that because you have complete vision. But if you didn't, you might have a memory of that. But the important thing about a reflex agent is it doesn't consider the future consequences of its actions. So in particular, it doesn't have a model of how the world will respond to its actions. And that means it can't simulate or predict into the future. Okay, reflex agents only consider how the world is. So let's see an example of a reflex agent. First of all, we talked about this last class. Can a reflex agent doing these kind of very simple input-response behaviors, can it be optimal? Can it be rational? Can it achieve its goals in a maximal way? What do you guys think? Yeah, sure. So let's see an example. Here is a reflex agent. Whoop. Okay. This reflex agent has been programmed to move directly towards north, south, east, or west, towards the closest dot, where that closest is measured in Manhattan distance. So what do you think it's going to do? Can't do any better than that, right? So that's a case of reflex behavior giving rise to optimal action sequences, even though there's no complicated thinking about what will happen if I eat this dot, what's next. This agent isn't planning, it's just reacting. Okay, so what you just saw there was a very reactive agent. That can get you into trouble. So today we're going to talk about agents that plan ahead, and in particular, let's see what the reflex agent does here when it's programmed to go towards the closest dot. Okay, so far so good. It left some dots behind. Okay, so go towards the closest dot doesn't really get you there. This agent has gotten itself stuck because it can't, in order to make progress towards this next dot, it needs to actually move away from it briefly. It needs to think about a sequence of actions which will achieve its goal. So reflex isn't really the whole solution. What we're going to start talking about today are goal-based agents. Goal-based agents plan ahead. They ask what if. So in particular, a goal-based agent is going to have some model of how the world works. In a simulated environment like a Pac-Man game, that model can be perfect. You can know exactly how the Pac-Man world responds. In the real world, and say a robot walking around the world, it's an abstraction and it's an imperfect model. We'll talk about the consequences of that later. But in any case, a goal-based agent has some idea about what will happen if you take an action, and therefore the agent is able to plan a sequence of actions which in the end achieve their goal, even if the intermediate actions maybe make progress in the wrong direction. Okay, so you need to have a model of how the world evolves, and you need to consider how the world would be. This lecture is about how to do that, right? So let's see actually two cases of that same board where the reflex agent failed. So let's see, here is another one. This is going to be, again, this is going to be the same board. The goal here is to eat all of the dots. What this agent is going to do, so the first one is kind of a very reflexive agent. It just did whatever was right in front of it. This agent is going to think ahead, but this is kind of a one day at a time Pac-Man. What this agent is going to do is it's going to find the closest dot, and then rather than moving directly toward it, it's going to pathfind to that dot. We'll talk about pathfinding in a couple slides, but it's going to find a path to that dot, eat it. Once it gets there, it's going to replan. So this agent is making plans to the next dot, right? But it's not thinking about what will happen after that. So it's a short-term plan. So let's see what it does. Right? Probably should have not left those dots behind. So, but at least it's not getting stuck. So one day at a time, Pac-Man does make progress towards its goal, but it's not kind of globally optimal. But you notice it was pretty fast. Let's look now at another. So why might you do something like that? That's, by the way, what's often called a replanning agent. It takes some actions, and then it plans again once its current plan runs out, or if its current plan is interfered with. OK, so let's see. Plan slow. You probably know what's going to happen already. All right, so right now nothing's happening. There's no computation happening. When I hit this key, this Pac-Man, this is Mastermind Pac-Man. This Pac-Man is going to plan to eat all the dots in the absolute most efficient way. Let's see what happens. Well, the first thing that happens is it's hard to be Mastermind Pac-Man. You have to think a lot, right? So Mastermind Pac-Man is thinking. Mastermind Pac-Man is still thinking. OK, so while Mastermind Pac-Man thinks, let's try to figure out why this is so hard, right? To just get from one point of the board to the other seems to be a really easy problem to solve, and then you can do it over and over again and kind of achieve your total goal of eating all of the dots. But this problem where we try to eat all of the dots in a mastermind way seems to be really hard. Today we'll answer why that's so hard, but maybe you can start having some ideas about it. All right, any second now, he's going to launch his master plan. OK, it's actually kind of impressive in the end. Right? Smart enough to not go down the dead end until the end. Okay, good job, Mastermind Pac-Man. Too bad you're so slow. Okay. There are a lot of reasons why you don't plan all the way till the end of time, right? You guys plan your day out, but you probably haven't planned out every single day till the end of your life, right? And the reason you don't plan too far into the future, on one hand, it's really slow, and on the other hand, something's going to disrupt your plans and cause you to replan anyway. So if there were ghosts here, if this were an adversarial game, we would have other reasons to replan aside from just the computational ones. All right, so how are we going to achieve our plans? Well, one thing we've seen is there are multiple notions of what is your goal and what is a solution to that goal. If my goal is get to that dot right there, that's an easy problem. If my goal is eat all of the dots, that's a harder problem. So there are multiple search problems. Each search problem that we phrase, okay, some of them are small, some of them are big. When we phrase a search problem, there'll be two parts to the solution. The first part is formulation. We describe the problem we're trying to solve in this generic search framework. That's formulation. Then the other part is solution. We take an algorithm like possibly breadth first search, but we'll have better ones. You take some algorithm off the shelf, and you feed it your formulated search problem, and it then finds the optimal solution for you. So there's formulating the problem, and then algorithms that solve the problem. First, we're going to talk about formulation. So what's going on here? What is a search problem? A search problem is the following thing. So if on an exam or homework you get asked, formulate a search problem, these are going to be the blanks you fill in. The first is a state space. This is a set of configurations of the world. We'll see lots of examples of this, but for example, here it might be a configuration of the Pac-Man board. That has a Pac-Man position, it's got some dots, maybe there's some ghosts. Though for now, we're going to be talking about single agent search, which means we can ignore adversaries. Okay, so there's a state space. Usually there are a lot of states in interesting problems. There's a successor function. The successor function tells you, okay, given a set of actions you can take, a successor function from any given state says, here are the actions you can take. Possibly, here are the costs that they will cost you. Sometimes there are no costs, and then all costs are 1. So it tells you, here are the actions you can take, here are the costs of those actions, and here is how the world will be after you take this action. So for example, if you see down here, if you're in this state and you go north, you can see Pac-Man's moved up and one of the dots has disappeared, right? So the successor function tells you what you can do and what will happen. right? So if you're actually building a search problem, you have to write code that says, here's the set of states. You have to write code that, given a state, lists actions, and given an action, tells you the response. This is what you have to do to formulate a search problem. All right, so there's a state space that tells you how the world can be. There's a successor function that tells you what your actions do to the world. And then there's usually a start state, which is how the world is right now, and a goal test. Okay, it's not a goal state, because often you're happy with, for example, eating all of the dots regardless of where you end up. There's a goal test that tells you which states of the world solve my problem. So Pac-Man is here might be your goal test, or all the dots are gone. Whatever it is, it's problem specific. So this is a search problem, state space, successor function, and goal test. And then, given a search problem, a solution to that problem is a sequence of actions. It's usually called a plan in AI. It's a sequence of actions or a plan which transforms the start state to the goal state. So a sequence of north, south, east, and west, which when you execute them all the dots are gone. That's what Mastermind Pac-Man does. Any questions on this? Okay. Let's see some examples of search spaces, and then we'll talk a little bit more about formulation. Then we'll talk about algorithms that solve these things. All right, so here's a map of Romania. This is a very abstracted map of Romania. I have not been to Romania, but I imagine they have more roads than this. These are the big ones, and this is therefore planning at a very high level of abstraction. If you were actually, an agent in this environment, you might plan at a lower level of abstraction. When you're actually driving, you actually swerve and avoid the potholes. If they have those in Romania, I wouldn't know. So let's imagine that your goal here is to get from this city here, Arad, to Bucharest so that you can fly out for your flight. Well, here's a map. This is kind of a human interpretable description of the problem. But what will we provide to the computer? Well, there's some state space. If my goal is to get from one city to the other, what might the state space be? What are the states? Well, they're the cities, right? That tells you where you are at a given moment. You're actually at Arad, but the other states are states you hypothesize being in while you do your search. So the set of states is the set of cities. The successor function, what determines the successor function? Okay, well, that tells you from a given city where you could be next. That's the roads. And your successor function essentially says, at a given city, the actions available to you are the roads that are exiting from that city, and they, in this case, have a cost. The cost is the distance, right? And this is a search problem where cost makes sense. Right, maybe it shouldn't be distance, maybe it should be time. These are the questions you answer when you formulate a search problem. State space is cities, successor function is roads. There's a start state, which is you start off in the city of Arad. And there's a goal test. What's the goal test? The goal test is the state that you're in Bucharest? So that is a formulation of a search problem. You feed that into your search box, and it'll produce a sequence of roads that transform being in Arad to being in Bucharest. And it might have some nice property like you get the shortest solution or something like that. We'll talk about that later. Okay, so this is kind of the simplest, easiest, classic case of a search problem where you're basically pathing from one place to the other, and the states are locations, right? It's really intuitive, and actually one of the big problems that people often have learning this material is that there are search problems which look nothing like this, and you have to make sure that you abstract away from just everything being pathing, okay, even though it makes a good demo. All right, so what is the solution? We talked about that. It's a sequence of road. So what's in a state space? You'll have practice as soon as sections and then on the first written assignment in formulating search problems. So what's a state space? Well, there's kind of an ambient, whatever you're doing, there's some kind of ambient state space that exists, and that's the world state, right? So in a game of Pac-Man, the world state is the kind of exact position of Pac-Man, the exact positions of the dots, which dots have been eaten, what direction Pac-Man is facing, anything else that is variable about the world. Actually, a Pac-Man world state isn't that big. But think about the real world. Think about the real Romania. The full state of Romania, well, it's like some quantum description of the whole country, right? So there's this actual world state. You would never plan over the world state if you could possibly avoid it, because that state space is too big. So instead, what you do is for every search problem, you formulate the smallest state space that allows you to make your plans. Right, Mastermind Pac-Man needs a bigger state space because he's got, bigger goals of world domination. Okay, so what is in your search state space? Well, it depends on the problem, and kind of a rule of thumb is you want only the details that you need from the world state that are necessary to support your search process. So for example, if your problem is pathing, let's say we're in the Pac-Man domain, and you want to path from your current state, right, where Pac-Man's here, and you would like to you're just desperate to get to this position. Maybe you want to eat that dot. It's super tasty, right? I don't know why. You want to get to that position. Now you have a pathing problem. Well, in a pathing problem, what you want to think about, there's a process you go through when you think about formulating a search problem. What you think about is you think, all right, well, what am I trying to accomplish? What's my goal test? What actions are available? What do I need to keep track of in the world in order to solve my problem? For this problem of pathing, the states can just be your XY locations. How do you know that's enough? How do you know you don't need to keep track of dots and stuff like that? Or how do you know it's not too much? Well, you can kind of think, what are my actions? I can go north, south, east, or west. By the way, if you have 4 actions, that's sometimes referred to as a branching factor of 4, because there are 4 things you can do at every state. All right, so your states, here are your actions. What is your successor if you're pathing? Well, if I'm at a certain location and all I care about is pathing, then after going, say, north, I can just update the location to be 1 square north. I don't need to worry about whether or not I just stepped on a dot and ate it. I don't need to worry about any of that because that's not part of my search problem. Okay? The goal test. What's the goal test for pathing? It's, is my location right there? Well, if the goal test is just, am I at a certain location, then maybe these states being locations is enough. And in fact, this is all you need out of this world state in order to path from one point to the other. In particular, you don't need to keep track of dots. Any dots you do or don't eat are irrelevant to the problem of pathing. And you say, but wait, I like dots, right? Then maybe your problem isn't pathing. Maybe you're trying to be Mastermind Pac-Man. If you're trying to be Mastermind Pac-Man, then your problem is the much, much harder eat all the dots problem. And now you can think, well, what's the goal test for that? It's not, I am at this location. What is the goal test? Right? It actually doesn't care about the location. The goal test for this problem is all the dots are gone. So your state space, since you're going to be applying the goal test to states, it better be able to support, are all the dots gone? So you might think, all right, well, maybe my state space will be something like number of dots left. All right, well, that supports the goal test, right? But let's say you're in the state of having 18 dots left, and you move north. How many dots are left? I don't know, right? Because you haven't put enough information into your state space in order to support that. So all right, well, what do I actually need? Well, in order to be able to tell whether or not my motion ate one of the dots that's remaining, what does my state space need to include? It needs to include my current position, just like the pathing problem, and it needs to include the entire information about not just how many dots are present, but which ones are present. So one answer to this problem is that the states you include are XY for the Pac-Man's position, and a Boolean of which dots are true or false, eaten or not, or present or not, however you want to set it up. This is a much bigger state space. We'll talk in a second about how much bigger. For this problem, you have the same actions, but they do something different. So now your successor function not only updates your location, right, it has to change your XY, but it also, if appropriate, eats a dot if you moved on to a location that has a dot. So this problem abstracts away less from the real world and therefore permits more powerful reasoning. The price you pay is computation. Okay? And then the goal test is the dot vector is all false. Okay? So when you get a formulation problem, you want to think, what's my goal test? All right, that information better be in the state. Okay? What do I need in order to do my successor function? What do I need to track? And that thought process will let you figure out the minimum necessary to pull from the world state in order to admit your search problem. Any questions? Okay. All right. So now for the bad news of search. Here's a world state in Pac-Man. There might be this is a 10 by 20 grid that Pac-Man's on. There aren't dots in every square. So there are 120 agent positions. There are 30 foods right now. 30 foods, I don't know. There are 30 pellets, and the ghosts can be in 12 positions each. Now, probably you're thinking in the back of your head, the ghosts are pinned into some weird cage, I can ignore them, and congratulations, that's a correct abstraction for most search problems you would have. Now, if you were doing kind of ghost gazing or something, suddenly the ghost would be relevant. All right, your agents can be facing north, south, east, or west, but that's kind of something that matters for the graphics engine, but not really for the planning process, right? So let's think about how big the world state is. Well, let's do some combinatorics. How many world states are there? Well, there are 120 agent positions. Okay, and then for any agent position, let's think about the food. right? How many food configurations are there? What do you guys think? 30? 2 to the 30? How many people think 30? How many people think 2 to the 30? Okay, 2 to the 30 wins. In fact, it's correct. So what is 2 to the 30? Uh-oh, I actually think this may be wrong in the slides. Anyway, 2 to the 30, because for each dot, it could be present or absent. If this starts feeling like bad news to you, that's a good intuition you have. All right, how about ghost positions? Well, ghost number 1 can be in any of 12 positions, and there are 2 ghosts, so that's 12 squared. And then, of course, Pac-Man, though this is irrelevant for any planning, Pac-Man can be in 4 different positions, 4 different faces. Okay, so that's a big number, and so this is why you don't plan in the world state. And that's just a tiny square of Pac-Man. That's not even any kind of realistic robot planning. All right, so lots of world states. Oh, it is right. Good for me. All right, so states for pathing. Remember, pathing was just the xy coordinates of Pac-Man. So how many states in the pathing problem? 120. Ghosts don't matter, directions don't matter, food doesn't matter. It's nice to be pathing Pac-Man. That was 1 day at a time Pac-Man. All right, so there's 120. How about eat all the dots? It's somewhere in between, right? You got to keep track of which parts. You need to keep track of the 120 positions and what else is in your state space. You need that 2 to the 30. Oh, it hurts, right? Okay, so that's it. It's not, you could ignore the ghosts, you can ignore the factor of 4, but it's still bad news, and that's why Mastermind Pac-Man is so brave, so powerful, and so slow. Okay, so all right, so how do we actually solve these problems? Well, we've talked about formulation. I'm going to move on now from formulation. I'm going to assume that there's a generic search problem, right? Somebody has defined it for you. What's it look like? Well, you have no clue what's in the search problem. All you know is the search problem. Think about it object-oriented programming style. All you know about the search problem is you can query the start state method and you'll get some object, right? This object could be a Pac-Man board. It could be a city in Romania. It could be a configuration of airplanes. You have no idea what's in the state. All you can do with it is what? You can call it successor function, right? And that will lead you to other states on which you can only call their successor function and evaluate the goal test. So think about it now. We're done with formulation. That's in a box. All we have now is some generic start state. States have neighbors from the successor function, and then some of them are magically distinguished as passing the goal test. All right, that gives us basically a state graph. So a search problem mathematically, if we think about it, is just a directed graph. The particular mapping from these concepts to the graph is that the nodes in the graph here, which I will call states. I won't call them graph nodes. You'll see why I don't call them that later. So the nodes in the graph, which are states in your search problem, the arcs in the graph embody what? What's that? That's the successor function, right? The costs would be weights on the edges. The actions kind of aren't specified. They would be labels on the arcs, so this would be a labeled graph. And the goal test, what's that? Well, it's some function that kind of likes to hang out with the graph that tells you for each node whether it's a goal or not. Okay, so basically, a graph is a mathematical representation of a search problem. For every problem, there's a corresponding graph. This one I've drawn on the PowerPoint. There is no search problem that is worth solving for which you can draw the PowerPoint of the graph, because these things are giant 120 times 2 to the 30th monstrosities. You can't even fit these things in memory most of the time, much less on a slide. Okay, so we can't build these graphs, but we know they're there mathematically, and we're going to need algorithms that find paths through these graphs without building them, because as soon as you've built it, that's bad news. These graphs are huge. Okay? All right. So what are we going to do if we can't build the whole graph? Right? You can't just build it and then feed it to your search problem. You've run out of memory, and you've run out of time, and you've run out of atoms in the universe, and whatever it is that you had, you don't have it anymore. Okay, so instead what we do is we take an idea that's going to show up over and over again in this class. Okay, there are particular special modifications of this we'll talk about next class for search. But here's the generic idea that will show up. It's really the backbone of the first half of this class. The idea is that you arrange your computation in a tree. That in and of itself should sound like something you've heard many, many times in many computer science classes. We're going to arrange our computation in a tree. This is going to be a tree of possible futures. Right? So you can think this is science fiction, this is your quantum futures of what could happen, except here you actually control all of the decisions. Okay, so what's at the top of the tree? Right? The top of the tree here is the start state. Okay, so start lives at the top of the tree. And then what are the children? Well, those are the actions that you can take from the start state. So what's down here in this row, these are the ways the world could be in one action. If you go further down, these are the ways the world could be in 2 time steps, right? 2 action steps. And so you can think of this tree as extending downward into the future, right? Among other things, what happens as you go downward to the size of this tree? It grows exponentially. So you think this tree doesn't look like, it's not like a triangle, it's like this, right? It just explodes. If you go too many rows down this tree, you're just sunk. Okay, so you need to be very careful about this tree. We don't build the whole tree either, because it's actually bigger than the graph. All right, but here's the basic idea. We're going to start at the top. We're going to push forward into the future while we plan. That's going to be search. And the idea is going to be we're going to try to do everything we possibly can to not build much of this tree before we find the solution hidden in the tree. Okay, so it's going to be about expanding this tree in kind of as cautious a way as possible, that's as efficient as possible. All right, so what's going on here is a what-if tree of plans and outcomes. The start state's at the root. The children are determined by the successor function. The nodes in the tree contain states, but as we'll see, a search state can be in the tree in multiple places because there are multiple ways of achieving it. So what a node in this tree really is a plan, right? This node here corresponds to the plan. I was at the start, and then I moved east. There are other ways to get into this position, perhaps. This node corresponds to that plan. Okay, again, for most problems, we can't build this whole tree. We dynamically build as little of it as possible on the fly. That's what search algorithms do, and that's what we're going to talk about next. Any questions? All right. Okay. This is the basic idea in search, right? It's a generic idea. It will subsume the breadth-first and depth-first search you already know, and also allow us to define new search methods that are much better. All right, so here's a search tree. What are we seeing now? This is that Romania problem. So you can see the root is the state of being at Arad, which corresponds to this root node in the tree, which is a plan for achieving being at Arad. What plan is it? It's the empty plan. Do nothing. You're already there. Okay? And as we go down into the tree, the plans get more complex. So here's how search algorithms are going to work. I'm going to do it in animation, then we'll see it in pseudocode, and then you'll see it in detail in your project ones, which should be up either today, probably tonight. Okay? All right, so here's the idea. All this green stuff is the mathematically existing search tree of exponential size that arrays out beneath you, but it hasn't been built, right? So that green stuff is just so that we know what's there mathematically. What's actually been built is just the root node. So here's what we do. We're going to expand out possible plans for achieving, remember the goal was to be at Bucharest. Key idea, we're going to maintain a fringe. The fringe is the set of plans that we're still entertaining. It's the set of plans that we might expand and that may or may not achieve our goal. So right now we've got one plan on the fringe. It's the plan, do nothing, congratulations, you're at Arad. Okay. Now we're going to expand down. So the basic flow of tree search is you take off of this fringe, right, the things you've built, you take a plan off the fringe, and then you put its children onto the fringe. Okay, so off pops Arad, and onto the fringe go these 3 plans. One where you take the road to Sibiu, one where you take the road to Timișoara, and one where you take the road to Zurand. So now we've got 3 things on our fringe, and we've got a choice. Search is all about making the right choice. Okay. One choice, possibly not the right one, would be to take the Sibiu node off of the tree, out of the fringe, put its children on, and as you can see, as we do this, we're going to expand downward in possibly some kind of ragged way. The search algorithm will determine how we actually expand, and the fringe is going to grow. When we pull something off the fringe and we see that it passes the goal test, that's our solution, and we return it. Okay? Everybody get the basic flow? Here's some pseudocode. Mostly this is here so you can look at it offline, but I want to point out the important ideas that are in the pseudocode. So first of all, what does tree search do? You pass it a problem. What is a problem? It's a start state, it's a successor function, all that good stuff. Okay, you pass it a strategy. The strategy is the thing that tells you, given a whole bunch of stuff on the fringe, which one you try next. The strategy determines the method in which you push your way downward through the tree. Okay, you already know 2 strategies, the depth first and breadth first ones, which we'll see in this format in a second. All right, so you start off by basically the thing in your fringe is just the start state, and then you do the following. If there's nothing in your fringe, then there's no hope for you and you fail. Okay. If there's something in your fringe, you take something off the fringe according to your strategy. Obviously, there are smart things and dumb things to do, so you better get a good strategy. If the thing you've removed from your fringe is a plan which achieves your goal, then you're done and you return it and it's a solution. Is it the best solution? Who knows, right? That has to do with analyzing the algorithm, and that's going to vary from strategy to strategy. But it's a solution. All right, if you've pulled something off the fringe and, as is typical, it is not the solution to your problem, then you throw it out, but you put its children on the fringe, and in that way push downward. Okay, so there's always going to be a kind of frontier of what you've explored going downward. So the main question is, which fringe nodes should we explore at any given time? And this is going to open up the world of search algorithms. All right, we're going to do one of my favorite search algorithms. It's on this graph, which, remember, is a silly example because you always know you've got a silly example of a search problem when you can see the graph, right? Real problems are too big to draw. But there's the graph. And what we're going to do is we're going to do a tree search on this graph. And I'm going to start it off for you. At the beginning, there's the root, and that's this node S. And over here, I'm going to keep track of what's on the fringe. So what's currently on the fringe? Well, there's the empty plan that achieves S. All right, we're going to do a kind of search which is difficult to implement. It's called CS188 guided search, and you're going to tell me what to expand. What should I expand? So let me write fringe. Fringe. Okay. What should I expand? Well, this is easy. The only thing on there is S. So I pull that off, and I put its children on. In terms of tree search, that corresponds to putting on, kind of growing the tree downward, and now I've got what? I've got P and E and D. Okay, and what's on my fringe? Well, these three nodes are on my fringe, but if I wrote them out, I would probably write them something like S to P, right? Because that node P there is actually not just, it's not just the state P, it's how I got there. Okay, in code, this would be done with back pointers. Okay, you'll figure that out in project 1. All right, so there's S to P, that's the one node. The next node is S to E. The next node is S to D. All right, what should I expand next? S to P? S to E, all right. No, okay, well, we're doing S to E, too bad. All right, so S to E, so now we expand, and what are E's children? Well, looks like there's H and R, and so those have to go on, S to E to H. The stuff on the right is really just the kind of leaves of the thing on the left, and then S to E to R. All right, CS188, which one should I expand next? Why are you telling me H? Okay, all right. R, so let's expand that one. S to E to R to F, right? So that adds this. And then what shall I expand? The most unruly class ever. All right. S to E to R to F to G, right? G is the goal node. All right, so now we expand this one, and before we get a chance to ask what the children are, the successors of G, we see that it passes our goal test and we're done. So thank you, CS188, or at least those of you who are not messing with me, for getting us directly to this very deeply buried goal while actually building very little of this tree. In particular, if this was procedurally generated, it doesn't matter how many children P has or how much is below that in the tree, we never touched it in our computation. This is kind of the ideal behavior. You get straight, kind of taken straight somehow to your goal, you're done, and you didn't have to touch this exponential monstrosity. Unfortunately, I do not know of a way of implementing CS188 search in code. Yes, question? How you implement CS188 search? I'm doing it the best way I know how. How would you do this in code? You can't. So we have approximations to this. Now the graphs I'm going to show you are going to, the PowerPoint I'm going to show you is going to show you two things at once. Don't get them confused. The thing at the top, the graph, has states in it, right? The nodes in this graph at the top are states in your search problem, and there's kind of arrows going everywhere. There's multiple paths in this graph. Each path in this graph, or each plan to the appropriate state, is a node in the tree. So the tree is like this graph unrolled from the start state. In particular, that means the tree's bigger than the graph. It can actually be a lot bigger than the graph. So not only is the graph big, you just made it bigger. Okay, we'll talk next class about how to avoid some of that. Okay, so I've drawn the entire unrolling of this graph below. But remember, only the things that get circled below are actually getting constructed, and many of them are then being thrown out afterwards. Okay, so right now, even though there's this whole mathematical object, this tree does not depend on the search strategy. It's just there, watching you, right? It's mathematical. What actually depends on the search object is how much of this you build. Yes? So you're asking kind of how does this all look in code? The way it looks in code is there's usually a data structure for the fringe. We'll talk about this in particular. Here the fringe will be implemented possibly as a stack. There are other ways to do it. There's a data structure. There are objects in your code which represent search states, right? And the only things you can do with that object in the basic case is ask for their successors. And there will be code which takes one of these state objects off of the fringe, takes the problem object, calls the getSuccessors method, and whatever objects pop out, they get pushed back onto the fringe using an add method or something. So this does all get implemented in code. You'll get to see that much more closely in the first project. Okay? All right. So let's see what we have. How many of you have seen depth-first search before? Okay. How many of you liked it? Okay, yeah, okay. There's a lukewarm, mild like of depth-first search. We'll see how that holds up. All right. So depth-first search, when you saw it, you probably saw it either as a recursive implementation where you kind of recursively call on children. That's one way to get depth-first behavior is to do recursion, right? Another way, you may have seen depth-first with the stack. That also gives you the same behavior. Right now, I'm talking about the behavior. The implementation is typically that the fringe is a last-in, first-out stack. That means when you push successors on, whatever you've most recently shoved into the fringe is the first thing out the door when you call getObject, right? So how would this work? What I want you to think about here is not the stack. I want you to think about the qualitative behavior in traversing the tree. That's what's important here. Well, at the beginning, you start at the top. In particular, depth first corresponds logically enough to a strategy which always takes a deepest node first. Which deepest node? Well, that'll depend on tie breaking and how your stack is built and blah, blah, blah. Okay, all right, so the deepest node to begin with is the start state. So its successors go on. The fringe is now D, E, and P, as shown here. The circles here indicate what's on the fringe. The redded out S, that means it's not on the fringe, but it's probably still available via some kind of back pointer. Okay? All right, what's the next thing I expand in depth-first search? Undetermined, right? I've got 3 options there of equal depth. There would be some behavior in your actual implementation. Let's say it's D. Now B, C, and E go on. Notice there are 2 copies. In a naive implementation, there are 2 copies of E. They're different nodes because they correspond to different paths, but there are 2 ways of getting to E that are sitting on your fringe. Use great care before you even think about messing with that property. We'll think about messing with it next class. Okay, what do I expand next in depth-first search? Well, I've got a choice, but I've only got 3 of them. Let's say it's B. All right, now I've only got one choice. It's A, right? And you're going to kind of move through in this way, right? Seem about right? Which goal will I find first? I'll find this one. Okay, at this point, notice that what is on the fringe, so at this point, what's on the fringe is just the goal, G, that path to the goal that's shown. All this red stuff is stuff that's kind of available by backpointer. Actually, some of this should be grayed out. It's stuff that's available by backpointer. All the gray stuff to the left was stuff that we had once built, but it didn't work. Nothing's pointing to it, and it's kind of mathematically and garbage collectionally gone, right? So we touched a lot of stuff, but we don't have to hold it in memory. Okay, let's watch this again in time lapse. Okay, watch how depth-first search sweeps through the tree from left to right. Okay? That's the important behavior. It goes all the way down the left branch, and it sweeps through the tree from left to right. Don't forget that. All right. Which goal will it find? If there are multiple ways of getting to the goal, that means there's lots of nodes in here that say G. Which goal will depth-first search find? Kind of the leftmost. Right? Is that the shortest one? Right? Probably not. Okay, breadth first search. What does breadth first search do? In terms of a strategy, I know you already know breadth first search. In terms of a strategy, it corresponds to expanding a shallowest node first. There's some implementation that backs that, for example, a first in, first out queue. That means whatever's been on the queue the longest is going to be the shallowest thing if you set it up right, and it'll be out next. Okay, the new deep stuff you've just uncovered is kind of waiting at the end of the queue. All right, so let's watch breadth first search. I'm going to do it a little faster because its behavior is simpler. So S comes off, and its 3 children go on. What happens now? One of them gets expanded. Let's say it's D. What's next? Now E, now P. So we go left to right through this tree at a single level, right? So we've taken out the whole first stripe. Now what do? We do the whole second depth, then the whole third depth. Notice what the fringe looks like. The fringe is kind of an entire stripe through the graph. Through the tree, right? So in general, the fringe will be this kind of thing. A fringe will be part of one tier, in this case the first depth, and part of the next tier, in this case the second depth. Okay? You see that behavior? And you can kind of keep doing that. In particular, breadth first search through this tree kind of moves top to bottom along search tiers where you do everything of depth 1, then everything of depth 2, then everything of depth 3. That's the emergent behavior of breadth first search. Okay. Which goal will you find? I'm not going to repeat shortest, maybe shallowest, right? Whether or not it's shortest will have to do with weights and costs, and we've kind of been playing fast and loose and assuming there aren't any. But once there are costs, you're still going to get the shallowest thing. Whether or not that's the shortest, that's between you and your costs, okay? All right, so let's ask some questions about these algorithms. Let's talk about their behavior, and then let's see some demos, then we'll take our break. All right, so when we talk about search algorithms, here are the questions we ask. So we ask, is the algorithm complete? A complete algorithm is guaranteed to find a solution if one exists, okay, eventually, right? It doesn't have to be optimally efficient. It just has to be guaranteed that if a solution exists, it'll return it eventually. Optimal. Optimal means it's guaranteed to find the least cost solution, not just the shallowest one. Optimal only makes sense as a question if there are weights. Okay, we can ask about time complexity and space complexity. The short answer is the time complexity is always going to be bad news. But, you know, there's degrees of bad news. What are we going to analyze in terms of? I'll mention these particular numbers as we get to them, but there's going to be some number of states in the problem. Let's call that M or N. There's going to be a branching factor. Remember the branching factor? That's how many successors. It's not uncommon that the branching factor can be small, like in Pac-Man it's 4, but the state space is huge anyway, right? We can talk about the depth of the shallowest solution, the maximum depth of the search tree, and so on. I'll define these as we get to them. All right, so let's talk about depth first search. Probably the first search algorithm you ever thought of. We've decided that you have a medium liking of it. Let's think about its properties. Is it a complete algorithm? That is, if there is a solution, is depth first search guaranteed to eventually find it? Okay, I hear yes and no. Does somebody want to defend no? I think I saw your hand first before. Yeah, depth first search, there might be loops. You got to fear these loops. Okay, so here's your start state. Let's say that you can go from start to A, state A, and then you can go from A to the goal. Okay, any search algorithm will do the right thing. What does it take in order to do the wrong thing? Well, let me add a B just for kicks. You can do this with a loop too. What will depth first search do here? Well, who knows, right? It's either going to go straight to the goal or what? It's going to loop, right? And so depth first search, remember, goes straight down the left of the graph and then sweeps from left to right. Well, if left is infinitely long, then you never get past step 1. All right, so depth first search can be kind of a disaster. So is it complete? No. Is it optimal? No. How long could it take? Infinite. How much space could you use during that infinite time? All of it. Okay, so depth first search is not looking so good. Now, the real reason why it was so bad is because of infinite paths. So we can really just kind of remove them. How do we remove them? We can't really go along saying graphs, we can only work with acyclic graphs. That's not going to work. Interesting problems always have cycles, but we can do something to prevent cycles. There are 2 main strategies for them. I'm going to tell you the one that you'll probably never do. first, and then I'll tell you the solution you probably will do next class, which is called graph search, which will work for all search problems. All right, so the simplest thing to do with depth-first search is to add what's called cycle checking, which means as you do either your recursive descent or as you monitor your last in, first out stack, you keep track of cycles. In particular, what you can do is when you expand a node and ask for its successors, you can zip back up to the root and check to see whether any of them are already on the plan, and just don't bother with them. You discard them. I'm not going to give you pseudocode for this because you're not going to implement it, but basically you add some hook that makes sure that when you expand things, you never allow a cycle into a path. Okay, now you might ask, why would you do this instead of graph search, which we'll learn next time? The answer is it's much more memory efficient, but you probably won't do it anyway. In any case, with cycle checking, depth-first search becomes complete. Okay, also with graph search, it becomes complete. Let's think about what a tree looks like. Well, you've got a start state here, so that's start. You've got one of those, right? What is the next thing down? Well, you've got some trees below, you've got some nodes below that correspond to all of the length 1 plans. How many of them do you have? Well, you've got B if the branching factor is B. What's next? What's below this? Each one of these guys branches out to B or something like that. So you've got B squared of them, right? So as you go downward, it gets bad, right? These things grow very quickly. The whole search tree, I'm going to draw it like a triangle, but remember, this triangle grows exponentially, not linearly as you go down. All right, so everybody get what this triangle is? It's the whole search tree, and it gets exponentially wide as you go down. How tall is this? How many layers can this have before you can't go any deeper? Without cycle checking, infinity, bad. Okay, all right. With cycle checking, how deep could you possibly go in a depth-first search? Well, you could have every state once on your on your plan. That's n, the number of states, but let's just say in general m, which is the maximum length path allowed in your search process. Okay, so you can go quite deep, and things at the bottom, how many things are down here? There's like b to the m, right? So now we can talk about depth-first search's properties with path checking, cycle checking. So is it complete? Well, m is a very big number. M is probably exponential, but it's finite, and so sooner or later you hit the left corner and you slowly move from left to right. So yes, depth-first search is in fact now complete. That's good, right? Is it optimal? Will it produce the shortest? No, it won't even produce the shallowest. It'll just produce what? Like the leftmost, right? What's the leftmost? Who knows, right? It produces something. How long could it take? Well, what does depth-first search do? Well, it kind of, let me change colors here. Depth-first search basically goes down the left here, and then it kind of sweeps through this graph in this kind of way, and at any given time, right, depth-first search has done the left half of the graph, and we're slowly moving rightward. All right, so how long can it take? Well, what's the worst case? Where's the solution? It's like down here, okay? In which case you'll have to basically compute the whole graph, right? And that means the number of time steps is going to be proportional to the number of nodes in this graph. How many nodes? Well, there's b to the m just on the last row. And if you add up all the others, they might be another factor of b on top of that or less, right? So it's going to be something like b to the m or maybe b to the m plus 1, right? How about space, right? And that's just a bound. How about space? This is depth-first search's one saving grace, which is even though I've taken all of this exponential time to sweep through the graph, at any given point, what is on my stack? Do you remember what the stack looked like? What is on my fringe? Right? It's just, let me find yet another color. Okay, so maybe this is the most recent thing. You're going to have its siblings, right, and then its parents' siblings, and then its parents' siblings, and there's going to be basically everything from where you're currently operating up to the root. You're going to have all future siblings in the successor functions upward. So how tall is this? Well, there's m here, and then for each of these nodes up to the root, there could be b siblings. So in fact, space is pretty good. Space is linear in m, though remember m could well be exponential. Okay, so the space is good, the time is bad. Any questions on depth-first search? All right. All right. When would depth first search be optimal? Can you think of any class of search problems for which depth first search is actually optimal? Not looking good for depth first search. Any ideas? Something like checkers. Well, checkers is adversarial. I'm going to set checkers aside for a second. Okay, what if all of your solutions were at the maximum depth, and they were all at the same depth? Well, and all the costs were 1. Well, then you wouldn't care what solution you had, and then depth first search would be optimal. And you say, but that never happens. Just you wait. It'll happen within 2 weeks. What does breadth first search do? Well, here's that same diagram. Remember what breadth first search does is it kind of computes, it'll compute this row, then this row, then this row, and so it moves downward in the graph. At any given time, you've done kind of the top of the pyramid, which is actually better than the left half of the pyramid because the pyramid grows exponentially, right? So you've done the top. How far down will you work before you stop? Well, it depends on where the first goal, here the goals are shown in red, is. And if the shallowest goal is at depth S, then you will compute downward in breadth first search, touching every single thing in this tree until you hit depth S. And that means that, that at this point you'll stop. So is it complete? Is breadth first search complete? If there's a goal, will you eventually get to it? Yeah, I mean, you could worry about things like infinitely many actions. The successor function returns infinitely many things. That's just bad news. Okay, assuming you have finite sets of actions and things like that, yes, breadth first search is optimal because you go from the top, you work your way downward, and sooner or later you'll hit the shallowest goal. It's complete. Is it optimal? Well, it's sort of optimal, right? It's optimal if the costs are all 1. In that case, shallowest is shortest, you get the shortest. Otherwise, you just get the shallowest. All right, what about the time? Well, remember, depth first search was b to the maximum length m, which is very bad. Here, it's b to what? Here, it's going to be b to the s, and maybe we'll throw in a +1 just so that we don't have to worry about all the work we did to get there. How about space, though? So what's on the fringe here? What's on the fringe is going to be something that's more or less an entire tier of the search tree. At any given point, you're going to have the last part of one tier and the first part of the next tier. Okay, how big is one tier? Well, it's this big. So at the time when you found the solution, an entire row, an entire tier of the search tree was on your queue, and that means you get exponential storage for the fringe. That's breadth first search. Any questions? All right. We're going to see what these things do. We're going to see a demo, and then I'm going to switch gears and talk about costs and heuristics. All right. So when would you choose breadth first search over depth first search? What is a qualitative scenario you might be in where breadth first search looks better? Well, maybe you want to find the shallowest goal. It's a kind of notion of shortest cost, right? So maybe you want the shallowest goal. Yep. Optimal is in terms of the solution returned being the shortest solution. Optimal in terms of time is a notion called optimally efficient, and it is very hard to define compared to optimal length, which is just there are a bunch of solutions. Is this the shortest? Okay, optimal here is not time efficiency. If you are interested in time efficiency, you're going to be sad in this class, because almost everything we do is NP-hard. Okay. All right, so when is breadth first search better? Well, when the goals are shallow, right? If the goals are shallow, then you don't want to be striping through the entire depth of the tree. All right. When you want the shallowest goal, when would you want depth first search? Kind of never, right? But maybe if memory were a real concern, or if you knew that all your solutions were at the same depth, and we will see an example of that. Okay. All right. So you should understand these trade-offs. All right. I'm going to show you a demo, and then we're going to see a new kind of search. All right. Here is the easiest search problem ever. You are trying to get from the green square to the red square. Okay. I'm going to execute a mystery search strategy, and what you will see is you'll see dots appear. What dots mean is the state corresponding to that square was expanded, meaning we got to a version of it in the tree and asked for its successors for the first time. And you get to tell me whether you're observing behavior that looks like breadth first search or looks like depth first search. So let's see. What's that look like? Breadth first search. How do we know it's breadth first search? Well, it's got the hallmarks. Things kind of radiate out in a uniform way. We did find a shortest path, a shallowest path, right? Here the costs are all 1, so that's also shortest. And you'll notice that in the process of exploring, we kind of went just as far in the wrong direction as in the right direction. Breadth first search just explores outward uniformly. All right, I guess process of elimination will make this simple, but let's see what depth first search does. Oh, depth first search. Yeah. Okay, so now you can see why people often like to make fun of depth first search. It did something strange. Okay. All right, let's now, I'll tell you one more thing just to file away, and then we'll take a break. The one more thing is there's a way of getting the best of both worlds. It's called iterative deepening. You will not implement this for your project 1, but when we talk about game tree search, this will be super important. Iterative deepening, get this, get ready for this. It runs breadth first search using depth first search. Okay, what you do is you do a depth first search which stops at length 1, which is basically just check the children of the root. If that doesn't return your solution, what do you know? You know there's no solutions of depth 1. You do depth first search with a length of 2. If you find a solution with max length set at 2, you know it's not max length 1 because you already did that, which means it's exactly length 2. So you've essentially done the second tier. And then you keep running depth first search with larger and larger max lengths until you find a solution. This does what breadth first does, but it gets depth first memory properties. And this is a cool thing to have in the back of your mind. Okay, it'll be important when we talk about game search. All right, before I talk about costs, let's take a quick break. So let's take a quick stretch break, 2 minutes, and then we're going to get started again. Okay, let's get started again. Pass. All right, let's start. All right. Now, so far, you knew all those search procedures. You knew depth first and breadth first search. And breadth first is actually pretty reasonable if you don't have costs. It's the problem with it, if you remember, is that it expands out in kind of all directions and therefore spends just as much time going in the wrong direction as the right direction. And that's something we're going to try to fix. The first thing we're going to do is we're going to figure out how to do something a lot like breadth first search with costs. And then next class we'll add heuristics to this, and we'll get an algorithm called A-star search, which does the right thing with costs and tries to focus the work in the correct direction. So that's a quick preview. Okay, now let's look at our example graph again, and here there are numbers. What these numbers mean is they're just costs associated with the edges, and now the notion of optimality or of shortest path has a meaning separate from shallowest, right? So in particular for here, the shortest path for the goal is what? It's start to E. Let me draw it out for you. The shallowest path is start to E to R to F to goal. And what is the shortest path? Looks like the high road. Okay, the high road is shorter but not shallower. Okay, and that's perfectly fine. It can be a longer path but still cheaper. We would like an algorithm that is capable of doing the right things when costs are present. So, uniform cost search. It is a lot like breadth first search, and you'll see why. Well, the rule here, it's still fringe-based search. You've got some stuff on the fringe. You're just going to change the strategy that you use to choose what to expand next. The rule here is you expand things in terms of cumulative cost. Whatever has the lowest cumulative cost, that is whatever plan, if you sum up all of the actions that get there, has the cheapest value. So at the beginning, the only thing on your queue is the empty plan, which achieves the start state. It has cost 0. It comes off the queue. What goes on the queue are these same three options, start to D, start to E, start to P, except now notice they have costs that came from the graph. Which one is the cheapest? Right, that's not shallowest, it's not deepest, it's whichever one's cumulative cost is smallest, and that is now the path to P, which is of cost 1. So I'm going to expand that, and its child here is going to go onto the queue, and what cost will this have on the queue? Well, we have to look. That's S to P to Q, so 16, right? Everybody with me? Not if you're with me. Okay, good. All right, so let's see if PowerPoint agrees. Great, so now what's on our queue? We've got S to D of total cost 3. We've got S to E of total cost 9, and S to P to Q of total cost 16. That 16 is a big number. That means this one's going to sit for a while. What's next? The next thing off the queue is this one, the path to D of cost 3. Its children go on, and each of them has a cumulative cost which has been incremented by whatever the search problem tells us. What is currently the cheapest thing? S to D to B. We're going to pop that one off. It has a child, A, here. And what's cheapest now? Now it's over here is where the cheapest one is. And so we're hopping around the tree based on the costs, and we're kind of pushing downward. I'm going to accelerate through this. Here, the next thing we would expand is R. No, sorry, A, which doesn't have any children. Next is the path through R. What's next? F. All right, look, the goal is on the queue. Everybody knows this. This is a critical time. The goal has just entered the building. It's on the queue, but we are not done, right? Goals can be on the queue. Don't get excited. Okay, the goal is on the queue with cost 10. What is the next thing we expand? E, right? All right. So, and now what happens? Okay, now we finally get to the goal and we pop it. The reason the goal has to sit on the queue, we'll see examples of this next time, you can get the wrong answer if you get excited early. What you have to do is wait for a goal to be removed from the queue according to the strategy. All right, so here we have, the next thing off is this plan, and uniform cost search outputs the plan S to D to E to R to F to G, which is the high road. It is not the shallowest goal, but it is the shortest. We love a uniform cost search, right? Okay, now let's look at the order again. Remember how depth first search striped left to right, and breadth first search did these uniform, kind of row by row tiers? Watch what happens here and see if you can see the pattern. Do you see the pattern? Yeah, it's kind of hard to see a pattern. Okay, what uniform cost search does is it moves downward actually a lot like breadth first search, but it's in a ragged way. right? And in particular, we can write what are called cost contours. So red is all of the nodes of cost 0. Orange is all of the nodes, I guess, of cost up to 6. Green is the nodes of the next cost. And you can see that what we expand is everything in the red zone, then everything in the yellow zone, and then everything in the green zone. And we are moving downward, and we're doing it like breadth first search if the graph were kind of stretched in a way that matched the costs. So we do move downward, but not in row. We move downward in cost. So we do have a kind of top to bottom, but areas of the graph that are cheap, we go deeper into the graph, and areas that are expensive, we stay shallower in the graph. So up here, we didn't go any further, but here things were cheap and we kind of burrowed down. So everybody got that? That's going to be very important next time. Yep. This is a great question. Is this Dijkstra's algorithm? Those of you who have seen CS 170 know Dijkstra's algorithm. This is almost Dijkstra's algorithm. Once you turn this into graph search using a very, very small trick from next class, this will be exactly Dijkstra's algorithm. Okay. Just in the way that we took breadth first search and we put it into our generic framework, this is Dijkstra's algorithm in our generic framework. Any other questions? Okay, so quick refresher. In order to build this in code, you need a data structure that lets you put things on it with a priority, and you need to be able to pull things off that have the lowest or highest priority depending on how you set it up. That's a priority queue. How many of you have seen a priority queue? How many of you liked it? Okay. Oh, you like priority queues better than depth first search. You're a smart class. Okay. All right. You can check that out. What does this do in terms of optimality? Well, we can kind of think our way through it now, right? So is it complete? Well, breadth first search was complete because it does the first row, then the second row, then the third row, and eventually you get to the nth row, whatever row the shallowest solution is on. How about this? Well, what are we going to do? We're going to kind of expand like to here and then to here, and it's going to kind of push downward in a cost-sensitive way, but it's still basically doing what depth first search does. Is it going to be complete? Are we guaranteed to get to one of these goals? What could go wrong, right? Well, what could go wrong is you could, in following costs, you could go like infinitely far down in some bad part of the graph and never make progress in the other part of the graph. Can that happen? Well, maybe if there was some chain that got kind of cheaper and cheaper in some pathological way, right? There was some Zeno's path that kind of gets, each one is half the previous. So you could have some pathological behavior. What has to happen to break uniform cost search is it needs to be that actions can get arbitrarily cheap or can have cost 0. So provided you have a lower bound on the cost of the cheapest action, then it's just like breadth first search. You eventually move down however far you need to find the goal, and you've done it in a slightly ragged way, and the solution you get will not necessarily be the shallowest, right? But it will be the shortest. So it's complete, provided those caveats. It's, in fact, optimal. So finally, we have optimality. You might think we would pay a price for that. What's the time complexity? Well, it's kind of hard to talk about, but kind of how deep could you possibly go? Well, let's imagine that this goal, the cheapest goal, has cost C star. Well, how far down could it possibly be? Well, it depends on the cheapest action. If the cheapest action is epsilon, this thing could be C star divided by epsilon rows down. And then you could have had to explore everything up to that depth. So if you really work it out, it's going to be B to the essentially S, but S now is this C star divided by epsilon weird term. So if you see this in the book, that's what it's talking about. Basically, it's exponential in how far you go into the tree, just like everything else, and it's still bad news. The hope is that because you're being selective about where you go into the tree, it's not that expensive. Turns out, if you want much savings, uniform cost search won't give it to you. We'll need A star from next time. How about space? Well, just like breadth first search, the entire kind of periphery is on the fringe, and that means the space is also exponential in kind of whatever that depth works out to be. Okay, so still exponential, but now it's optimal. We'll worry about efficiency next time. Questions on uniform cost? All right, a couple more important things to set up next time. Let's see what this does. So what does uniform cost do? It's going to, just like breadth first search did kind of depth 1, depth 2, depth 3, uniform cost is going to do stuff of cost 1, then stuff of cost 2, then stuff of cost 3. So they're cost contours. If you start at a start state and you kind of watch what's expanding out in a graph that's visualizable spatially like this, it'll radiate everywhere. It doesn't know where the goal is. It just explores in all directions. Let's see this in a demo. So let's bring back our favorite empty blue square. Remember, this was, what was this? Breadth first search. What do you think uniform cost search is going to do? This is uniform cost search. It's not quite the same. It's kind of jumping around because the data structure is breaking ties in a much weirder way. But it does the same thing. OK, so let's get some costs in. Uniform cost search doesn't do interesting things until then. All right. Here's a search problem. You want to get from green to red. And blue costs, I think, 3 times as much as light blue. So dark blue is the deep water, right? It's more expensive. That doesn't make any sense. Dark blue is more expensive. All right, so let's see what, well, you tell me what I'm showing you. What am I showing you? Yeah, right. We love you, depth first search. All right. What's this? How do you know this is not uniform cost? Right, it is not sensitive to the cost. It's going out in kind of in squares, not in costs. So by process of elimination, this must be, oh, it's so beautiful. Okay, you'll notice that it expands outward to everything that you can get to in the cost that it takes to get to the red square. And in some regions, you can get quite far, the light blue. And in this dark region, you can't get very far before you hit that cost of the optimal solution. So you don't explore as much stuff in the expensive direction. That's uniform cost. What you'd really like to do is not spend so much time going to the left. And in order to get that, we're going to need heuristics. OK, so let's briefly see just a teaser about heuristics. We've seen what uniform cost does. We've seen what breadth first and depth first does. Here is how we're going to make progress. And the thing I'm going to tell you today is heuristics and greedy search, which is not optimal, and it usually doesn't work. OK, so here's the setup. A search heuristic, all of you know the word heuristic. Forget what you think it means. A heuristic in the context of search means something totally new. It's a function from states to numbers. And those numbers are going to be estimates of how far the goal is. It is not a rule of thumb. It is not something like go left until you hit the stoplight. It's not heuristics like stay towards the wall. A heuristic is like 12, right? I think I am 12 away from the goal. OK, so from here, from this state for Pac-Man, a heuristic is a guess, right? A function from this state to how far the goal is. You have to design these. So just like search formulation, they're not generic. They have to do with a specific problem. So what might I do? Well, you could say something like Manhattan distance. If I compute the Manhattan distance from Pac-Man to this dot, I will get 15. That is one possible heuristic, Manhattan distance. On this state, it returns 15. I could do Euclidean distance. It would give me 11.2. Which one's more reasonable? Right? In this case, actually Manhattan distance, because Pac-Man lives in a Manhattan kind of world. But these are just guesses as to how far away you are. What you do with that information, try to make progress towards smaller numbers, is the business of the search algorithm. All right, so that's a heuristic. Here's another heuristic. This is Romania again, and the search problem is on the left. The heuristics are on the right. This heuristic is the straight line distance from city to city. The numbers on the graph are the distances in the roads. All right, so you can see, for example, Bucharest has heuristic value 0, right? Your 0 distance from your goal. Arad, where you start off, has some other distance, and each of these cities has some number given by this heuristic, right? These numbers could be totally off. There's good heuristics and bad heuristics. Structurally, if it gives you a number for every state, it's a heuristic. Whether or not you like the numbers it gives you, that's a discussion for another time. What can you do with a heuristic? Well, let's think of a way of incorporating it into our search algorithm. Any proposals? Great. So prioritize nodes based on, so you look at the state and you see its heuristic value, and you expand next whichever option has the smallest heuristic. So of the things on your fringe, you look at your heuristic to guess which ones are close, and whichever one the heuristic tells you is closest, you expand it next. Okay, you're putting a lot of trust in your heuristic. Choose your heuristics carefully. All right, so let's see what it does. Yes? Great question. Do you have to consider states whose heuristics are larger than the shortest path or something like that? One, you don't know the shortest path in general. And two, the heuristic can be wrong. Starting next class, we'll have properties of the heuristic, like it has to be a lower bound. Right now, it's just some number. Okay, so I haven't given you any constraints on this heuristic, other than presumably if it doesn't correlate with reality, this search isn't going to work very well, right? All right, so expand the node that seems closest. This is called greedy search. How would this work? Well, at the beginning, you have Arad with priority 366, so you expand it. All right, let's go back and stare at Romania. The important thing about Romania, well, there are many important things about Romania. For the present purposes, the important thing is that there's a high road and a low road, and which one is shortest? Here, the low road is short, and the high road is shallower but long, okay? All right, so we want to go from Arad to Sibiu, not to Fagaras, but instead to Riminichu something. All right, so we're going to expand the node that seems closest. Here's Arad. Here are the children. So Sibiu looks like it's going in the right direction. We don't worry about Zerend, which is off in the other direction. We expand that, and we look, and everything's going so well, we're making progress. We see that Fagaras gets us closest according to the heuristic. Little warning sign, this is in fact not the optimal thing, but, you know, we're bold. Okay, so we're going to expand that, and we can see that one of its children is Bucharest. We expand that, and we've returned a solution. So on the downside, this is in fact not the shortest path, but on the upside, what's good? I think we got right there. Okay, and in fact, this is the caricature of greedy search. It takes you straight to the wrong goal, right? And when you don't much care about when you just want any goal at all, this can be a great thing. All right, so what does it actually do? Well, what can go wrong? How can things go wrong? Well, the heuristic can mislead you. There's actually some subtle ways, even if the heuristic is right, this can still go wrong. We'll see examples of that next time. But basically, if the heuristic isn't good, you're certainly out of luck. All right, what is kind of the best case is up here. The best case is that all you expand is stuff along the path to the optimal goal. You would love that heuristic, right? It takes you straight to the optimal goal. This is CS188 guided search, right? This is when you took me straight to the shallowest or to the shortest path without wasting time in the rest of the tree. What is this? So that's this. What's the worst thing that can happen? You can get taken on a wild goose chase. The heuristic can tell you that everything but what you're supposed to do is cheap. And you can explore the entire search space except for where the path to the solution. Okay, those of you who were telling me crazy stuff earlier, this is you. Okay, this is bad students. Okay, all right, so you can have good heuristics, you can have bad heuristics, and next time we'll see that even with a good heuristic, there's some subtleties that'll lead us to A-star search. I'm going to leave you with two things today. The first thing is a demo, and the second thing is a real-world lesson. All right, so demo costs. What is this? Do you recognize him? Uniform cost. What is this? Straight to the wrong goal, right? Notice this is not cheap, but it's fast. All right, so there's that. The last thing I want to leave you with is we talked a lot about algorithms, right? These algorithms, it's very important that you model the world in the right way. So how many of you have had a bad experience with something like an automatic mapping? You got directions, they weren't quite right. Here are some really bad cases. And then I want you to tell me why. Okay, so let's say you were trying to go from Trondheim to Haugesund in Norway. I'm sure you've many times had this problem. There was a time where if you had typed this into one of the leading map engines, you would have gotten the following path. Let's take a look at it. You start in Haugesund, you immediately go to England, and then kind of through mainland Europe. Okay, and then finally you end at your destination. So this is an example. This is a complete algorithm, right? It got you a solution when one existed. This is probably not the optimal solution, or is it? What went wrong here? Did they implement a bad search algorithm? Probably not. The search algorithm's great. What's wrong here? The model's wrong. There's some road missing. It disconnects Norway into two components. It's very sad. Okay, so your model has to be right. If your model's wrong, your search algorithm won't save you. Here's another example of this. This next one is an example of abstraction. If you go along saying kind of what is a road? Remember, we just had these big roads in Romania. Here, you get directions. You get told to go up Loma Vista Place. If you look closely, you'll see that Loma Vista is, in fact, about 2.5 feet wide. This is a case of planning at the wrong level of abstraction. If you want to have roads like this in your map, that's fine, but now your state space better include the width of the road and the width of the agent or something like that. So this is a problem with abstraction. Something else, just as a preview for later. What does Loma Vista look like? It actually looks a lot like a tree. This is important when we talk about automated driving. This is why automated cars like to drive up trees. Okay. Okay. We'll see you next class.